Welcome back, Apologia, Physical Science, Week 14, Day 3, textbook pages 232 to 235, notebook pages 190 through 192. This will also include Experiment 7.1, Acceleration Due to Gravity. We are going to quickly go over this experiment, but I do expect you to complete this entire experiment on your own at home. There really isn't that much to this experiment. Gravity. You just read that a force is a push or pull that acts on an object. Often, the push or pull causes motion. But do you realize that the force of gravity is the only force in which you do not need to push or pull something to get it moving? When you drop something, you need not push it. It starts moving all by itself. Why? Because of gravity. But what does gravity do in order to make a dropped object begin to move? If there is nothing holding the object up, such as the floor, a table, etc., gravity causes an unbalanced force and gives the object constant acceleration. Acceleration due to gravity. Whenever an object is falling towards the earth without anything inhibiting its fall, we say that the object is in free fall. The definition of free fall is the motion of an object when it is falling solely under the influence of gravity. In free fall, gravity accelerates an object. Without some force, such as air resistance, drag, inhibiting the motion, the object will continue to speed up because it is under constant acceleration due to gravity. If you drop a rock from a tall cliff, then it will continue to pick up speed until it hits the ground below. That's free fall. In order to learn something about the acceleration that objects experience while they are in free fall, conduct experiment 7.1. So the name of experiment 7.1 is acceleration due to gravity. All right. Experiment 7.1, acceleration due to gravity. The purpose of this experiment is to observe how acceleration due to gravity is independent of the following object. The materials: we need a heavy book. We got a pink heavy book. A small piece of paper about 3 centimeters by 3 centimeters. We've measured that out carefully. We have our paper. And eye protection, which my assistant is happily wearing right now. Thank you, assistant. Okay, background. One of the properties of free fall is that all objects experience the same acceleration regardless of their weight or physical makeup. That tends to go against your everyday experience. This experiment shows you that it is indeed true. All right, the question that this experiment's going to answer is, what happens when you drop 2 different objects at the same time? Do they hit the ground simultaneously? All right, so take this time to write what you predict will happen to the paper and the book when dropped from the same height at the same time. Do you think they will hit the ground together, or do you think one will hit before the other? Okay, I hope you had time to write your hypothesis. The procedure: hold the book in one hand and the paper in the other. Hold both of them out at arm's length. Okay, 1 second. Let's keep reading. And make sure that they are at exactly the same height. Make sure that there are no obstructions beneath the 2 objects so that they can fall to the floor without running into something. In a minute, when I'm ready to film, we're going to release them both at precisely the same instant. Note what happens. Specifically note which object, the book or the paper, hit the ground first, or if they hit simultaneously, note that. Okay, helper? You have both of them at the same height? Yep. Perfect. When you're ready, 3, 2, 1. Okay, so it appears as though the pink heavy book hit the ground first. Okay. So let's note that in the data table. All right. Step 3. Next, repeat the experiment in a slightly different way. This time, place the piece of paper on top of the book and hold the book out at arm's length with both hands. When I'm ready to film it, we're going to release the book and the paper. So you're going to place the piece of paper directly onto the book and then hold the book with both hands. And then when you're ready, on the count of 3.
2, 1.
They appear to both hit at the same time. Okay, so go ahead and write your observations down for step 3. Okay, so what happened in this quick experiment? In the first part, the book hit the ground first. That is what you would expect from your everyday experience. After all, the book is heavier than the paper. Thus, it should fall faster than the paper, right? Well, this leads most people to believe that gravity accelerates heavy things faster than it accelerates light things. After all, both the book and the paper were being accelerated by gravity as they fell. The book fell faster, so it must have experienced more acceleration, right? If that's the case, how can we explain the second part of the experiment? In that situation, the piece of paper stayed on top of the book, falling just as fast as the book fell. Well, why did this happen? The paper was not stuck or glued to the book, therefore it did not have to stay on top of the book. If it were really experiencing a smaller acceleration due to gravity than the book should have started traveling faster than the piece of paper, eventually pulling away from it. Instead, they both fell at the same rate. Why? They both fell at the same rate because they both experienced the same acceleration. Thus, the conclusion I just stated from the first part of this experiment is very wrong. How then do we explain the first part of the experiment? All right. The answer is fluid friction or air resistance. Remember, air is made up of gases, and as an object falls, the molecules and atoms of gas must get out of its way. Well, the molecules and atoms resist this movement, and the object must force its way through them. A heavy object is much better at doing this than a light object. Therefore, heavy objects fall faster than light objects, not because of their acceleration due to gravity is larger, but because they are not as strongly affected by air resistance as the lighter objects are. When we neglect air resistance, all objects falling near the surface of the earth accelerate equally. In fact, when we eliminate air resistance and drop an apple and a feather, they fall at exactly the same rate of acceleration. So when dealing with objects falling near the surface of the earth, we will always neglect air resistance. For most relatively heavy objects, this is a reasonable thing to do because air resistance does not affect heavy objects very much. Well, now that we know all objects accelerate equally under the influence of gravity, we need to know what that acceleration is. Near the surface of the earth, the acceleration due to gravity is 9.8 meters per second squared. In English units, that turns out to be 32 feet per second squared. These are numbers that you just have to memorize. The acceleration due to gravity for an object is 9.8 meters per second squared in metric units and 32 feet per second squared in English units. That sentence will be put on page 191 in your notebook. Whenever you do problems involving free fall, you will use one of those values for acceleration. Well, which one will you use? Well, that depends on the problem. If the problem deals with metric units, you will use 9.8 meters per second squared. If the problem deals with English units, you will use 32 feet per second squared. You will see what I mean in just a minute. It turns out that because the acceleration of an object experiences in free fall is constant, there is one neat thing we can do. If an object is dropped without being given any initial push, we can determine how far it falls, given just the time it is in the air. In other words, if we time an object as it falls, we can use the acceleration due to gravity to determine the distance it fell. We can do this by multiplying 1/2 times a, the acceleration due to gravity, times the time squared, as in equation 7.1. D equals 1/2 times A times T squared. Don't worry about where this equation comes from. You will learn that when you take high school physics. For now, you just need to practice how to use the equation. We're going to look over example 7.1 and see how we do this. All right, example 7.1. A young woman is standing on a bridge overlooking a river. If she drops a rock from the bridge and it takes 1.2 seconds for it to hit the river, how many meters did the rock fall? Okay, so step 1 is always write the list of knowns and the unknown. Since the rock is in free fall, we know it experiences acceleration due to gravity. And since the question asks for the distance in meters, you're going to want to use the acceleration due to gravity that has meters in it. So that it would be the 9.8 meters per second squared. Let's see. Check that all units agree, and if they don't, you must convert one to another for agreement. Okay, so we knew that at the time it took 1.2 seconds again, and we are using this acceleration, 9.8 meters per second squared. We're trying to find how many meters it fell, or the distance. Step 2, write out the equation. Use 7.1, that's the equation we just learned. 1/2 times the acceleration times time squared. Step 3, write out the equation substituting the numbers from step 1. You might find that using 0.5, which is the decimal unit for a half, is easier. Sometimes I think it is. So we have here distance equals 0.5 times A, acceleration, times time squared times time squared. All right, step 4, solve the problem. Remember that when something is squared, you take it times itself. So 1.2 squared would be 1.2 times 1.2. All right, so the distance that the rock fell was 7.056 meters. Notice what happened here. When you put the numbers into the calculator, you type 0.5 times 9.8 times 1.2 times 1.2. Now look at the units. A second times a second is a second squared, so the second squared in the denominator of the acceleration cancels each of the units of time. This leaves just the meters unit. Since distance is measured in meters, we know that the equation worked out the way it should. It turns out that this will always happen in physics and chemistry. When you use physical quantities and equations, the units will always work out like they did here. That's the reason the units in an equation must agree with one another before you can solve the equation. If they do not, units that are supposed to cancel will not be able to, and the answer will not make any sense. This answer, however, is not nonsense. The rock fell 7.056 meters. If you think about it, this little fact of physics can be incredibly useful. You can use time to determine the height of something too tall to measure. Let's talk about the On Your Own problem 7.4 to see what I mean. On Your Own 7.4. A stone is dropped from the roof of a house. A person standing on the ground watches and times the fall of the stone with a stopwatch. If the stone takes 1.1 seconds to fall, how tall is the house using feet as your measurement? Okay, so step 1 is always list what we know. We know the time is 1.1 seconds because it tells us that. It asked us to use feet as our measurement, so it only makes sense that we would pick the acceleration of the one that has feet in it, so 32 feet per second squared, and we're trying to determine the distance that it fell. We don't know. All right, step 2. What equation are we going to use? Well, 7.1 gets us exactly what we need to know. The distance is half times the acceleration times time squared. All right, so let's go ahead and plug in our values. So we have half times 32 feet per second squared times 1.1 second squared, or 1.1 times 1.1. The answer is 19.36 feet. So the rock fell 19.36 feet.